Okay, so this last rotation review question is probably one of the hardest ones I've seen, not mathematically, but just because it's so long and there's so many steps. And since it was just last year, I think it's probably a good one to practice. So this is one that you should make sure to work through very, very carefully to make sure that even if you can't do 100% of it, you don't get too overwhelmed by just the length and number of things, and you get the points that you're capable of getting. That's really the biggest challenge in this problem, I think. All right, so with that being said, the other thing that makes the problem tough is that the description is pretty complicated, right? It's a long paragraph, there's a data table, there's pictures before and after, there's multiple variables for everything. And so this is one of those questions where you really have to spend probably about as much time as I'm talking right here, reading carefully through everything to make sure you recognize keywords, like what's the equilibrium length of a spring? That's an important thing to find. How long is the rod? How big is your platform, your disc platform? Things like that. You have to know all those numbers before you can really start solving the problem, or you'll put variables in the wrong spots. So you'll understand what you're trying to do, but you won't know what numbers and letters to put there. So part A, we're asked to figure out a expression for the spring constant. So we want k equals some collection of variables. And we have a block of mass m going in a circle, right? It's attached to a rod and the spring combination, and it's going in a circle at constant angular velocity, right? So if our block is right here, if I look at figure 2, right, the block's at the top, and there's a spring force that pulls it back. There's also a weight force into the page and the normal force up out of the page, but those are going to balance, so the net force is only going to be the spring force, and it's causing it to move in a circle. So we can write Newton's second law. And the force is the spring force, that's kx, where x is how much the spring is stretched. We'll clean that up in a second. And a, I'm going to write in terms of angular velocity rather than linear because we're given that, right? Is that, omega squared r. So now we have to identify sort of what goes into this general statement. What is x? How far the spring is stretched? Well, where the picture shows that the spring is a total length of d over 2 and another d over 2, and the equilibrium length is d over 2. So the amount that it is stretched is just d over 2. And r is how far the block is from the center of the circle, which is the length of the rod, d, the length of the spring, which is also d. Right? So this is where being careful is so important. The other way you could get is right, the radius of the disk is 2d as well, and it's clearly on the edge of the disk. So that way works. So now we just need to find what k equals, right? Rearrange. The d's will cancel. We get k is 4m omega squared. Right? That's part A. Fairly straightforward. So part B has two little subparts, although one of them is really just to make sure you do this step. It's not really an extra challenge. So we need the rotational inertia of the block about the axis of the platform. Well, the block is essentially a point mass. And we know the moment of inertia is mr squared for a point mass. Well, block is mass m. Its distance from the center is 2d. So that's your moment of inertia. Right, that one's pretty straightforward, I think, as long as you remember the sort of definition of what moment of inertia is for points. The second part is then to figure out the moment of inertia of the whole system. And this one isn't too hard either, as long as you're sort of careful and organized. So the moment of inertia of the system is the sum of all the individual moments of inertia, which is just I block, which we just found, plus I rod, plus I platform. So all we need to do is figure out those three pieces, and one of them we just did before, right? So 4md squared, that one's done. Now the moment of inertia of a rod, we're given the rotational inertia of the rod in the table is the mass of the rod times d squared over 3. But the mass of the rod is given as 3m, so we have to substitute that 3m in. We can't use mr. So 3m d squared over 3. And the moment of inertia of the platform is much the same. We're given it in terms of the mass of the platform, but that's just 5m. So 5m. And then this one is r squared, but we know r is 2d, and divided by 2. Right? So now we just need to do some algebra to combine these things. Right? These 3's will cancel. This 2 will cancel one of those 2's, so we just get a factor of 2 not squared. So we get 4 from here, 1 from there, and 10 from this term, all times md squared, which is then 15 md squared. And that's the total moment of inertia of this whole rotating thing. And if we have that, part C is quite fast. Right? And once again, if you can't get the answer to part B, but you know how to use it in part C, you just do that. So we have something that is symmetric. It's not simple, but it is clearly symmetric, and it's rotating about a fixed pivot, so we can use L equals I omega. We just found I, right? We want the angular momentum of the entire system, so we have to use the rotational inertia of the entire system. So that's 15 md squared, and omega we're allowed to use as a variable, so that's really it. That's part C right there, recognizing that you can use that formula and then using your result from part B. All right, so that's all like the preliminary stuff. The next part involves moving the rod. So this is parts D, E, F, and G. So part D, we've moved the rod, now it's centered. It's no longer rotating about the end, it's rotating about the center of the rod. And so to keep going at a constant angular velocity, what's providing the force doesn't change, but the magnitude of the force does, because now we have a smaller radius. Right? So we still have a block, but the net force is the spring force. And since we haven't changed the spring constant can't have changed from what we found in part A. We can still write this, and a lot of it is still true, right? So this is kx. Again, I'm gonna change that x, because I think I'm going to use, I'll call it x prime for now, just to indicate it's not the same as the x that's labeled on the diagram yet. We haven't thought about it. It's just the amount the spring is stretched. And then m omega squared r. And so once again, we just need to figure out what r and x are. So we want x equals. So first thing is, what is x prime? The amount the spring is stretched. Well, that is actually x on the diagram. So I'm just going to leave it right like that. And now, how far is the block from the center? Well, it's half the rod, right? That's d over 2, half the rod, plus the spring's equilibrium length, plus how much the spring is stretched, right? That's how far the block is from the center now. And we can plug in what we know for k and solve for m. So this is d plus x. We divide by k, which is 4m omega squared. So we cancel lots of stuff, and we get x equals d plus x over 4, or 4x minus x equals d, or x equals d over 3. Right? So when we center the rod, now the spring, instead of being stretched a distance d over 2, it's now stretched a little bit less, d over 3, because it's a smaller radius to maintain the same angular velocity. So it all makes sense. Okay. So now, and this is important, right, another reading part, parts E, F, and G are sort of in the process in between figures 2 and 3. So the rod is moving very slowly towards the center. But it hasn't made it all the way to figure 3, but it's not where it was in figure 2 either, like the in-between part. And one thing that's important to note about these two parts, right, you're given a checkbox, so you should always pick something, But if you don't make an attempt at justifying, you don't get any points for the lucky potential guess you might have made. So you have to always at least try a justification. If it's wrong, but it's some physics relevant sort of concept, then you get at least the point if you happen to guess correctly. If you leave the justify part blank, then guessing doesn't help on these. So always at least attempt something. Even if it seems like it's gibberish, you might convince the examiner that you have some clue, even if you haven't explained it well. So, first thing, is the angular momentum of the system increasing, decreasing, or staying the same as the block is slowly moved towards the center? Well, we have our expression from before, and we have to just look at what changes. Omega, we are told, is constant. So what about the moment of inertia? Well, the mass is getting more concentrated towards the center, right? The rod is being a bit more centered, and the block is now closer to the center. So this is decreasing. And if that's decreasing, then therefore this must go down, right? So for your justification, you want to do something relating to that omega doesn't change, I get smaller because the mass is now closer to the center, therefore using L equals I omega, the angular momentum must go down. F. In order to keep the system rotating with constant angular speed during this whole process, is the motor doing positive work? In other words, is it adding energy to the system? Is it doing negative work? Is it taking energy out of the system? Or is it doing no work? Is total energy constant? Well, we have rotational energy, right? Everything that's happening is rotational. We're assuming that the motion of the rod sort of to center it is so slow that there's essentially no energy there. So the energy we have is that. And so we're going to do the same sort of process. Omega is constant. I is decreasing. So if I decreases, then the energy of the system must also go down as well. Therefore, the motor must be doing negative work. It does something to decrease the total energy of the system. So the answer to part F is that it's negative work, and you want to reference this equation and the fact that the moment of inertia is changing as your justification. All right, and finally, we have part G, which is basically just a free body diagram. We have the block sitting right there. Right, and so our center of our circle is like directly below it, and we're told that it's rotating currently right in that direction. And you're supposed to draw one single vector to represent the direction of the acceleration of the block. And I think most of this is somewhat straightforward, but there's one extra little trick in it. So the way I think about this problem is sort of what components do you have? And I'll draw the single vector at the end. So I'm going to use, the first thing that happens is moving in a circle. Therefore, there must be a vector that accelerates it toward the center of the circle. That one has to exist. So the question is there anything else? Is there any force that's tangential to the circle? And there must be. Because if omega is constant and r is decreasing, that means that the linear velocity v is decreasing as well. And that means there must be an acceleration that's tangential to the circle. There must be one that's like that makes it slow down, right? And so those are the two components that have to exist if the motion is going to be as it's described. And so the one single vector that represents the acceleration is the net force, or net acceleration, or sorry, net force, which is the vector sum of those. So it's going to look something like that. And so as long as you draw an arrow somewhere in that fourth quadrant area, you get that point. You have to recognize, right, it's doing two things, right? It's moving in a circle and it's slowing down, and those two directions of forces give rise to that one red net acceleration. And so this problem brings in a ton of different concepts, right? Rotational stuff, springs, non-uniform circular motion from way back in the early part of the year, energy conservation, angular momentum conservation, work, really essentially every single concept we've done. And you have to be prepared in rotation questions to put all those pieces together. So this is a really good practice problem.